reactive with base or acid loses water, and sometimes people call just the first step, so that's step A, the aldol reaction, and sometimes people, when they talk about an aldol reaction, include both of those steps. Now, what I need to do now is to say a little bit about a crossed aldol reaction. So let me first write up the name. In a crossed aldol reaction, what we mean when we use that expression is that the two carbonyl compounds are not the same. Now, obviously, if I take, let's say, this aldehyde and that aldehyde, so if I take those two, obviously, and treat them with a base, I could deprotonate this one, which could attack that, or I could deprotonate this one, which would attack that. So I get a mixture. But if you want to do a crossed aldol reaction, in other words, you want to use two different carbonyl compounds, then there are a few tricks that one can use in order to get just one product. And the obvious trick is to use one carbonyl component that does not have an alpha hydrogen, so that only one of them, let's say this one, can be deprotonated. And the way that that is done, or an example of how that is done, is the following. If we take this aldehyde and that ketone, acetone, and treat them with sodium hydroxide, what you can get is that compound in quite reasonable yield. Now, what is going on clearly is that this compound is being deprotonated. The benzaldehyde can't be deprotonated. There are no hydrogens on the carbon next door to the carbonyl. But in the case of acetone, there's hydrogens here and hydrogens here. Unfortunately, the molecule is symmetrical, so it doesn't matter if we deprotonate here or deprotonate there. Supposing we deprotonate here, the carbanion here can attack that carbonyl to give you an alcohol. You get the aldol product, and then dehydration occurs. Now, of course, deprotonation of this acetone to give a carbanion could react with another molecule of acetone that isn't deprotonated. But it turns out that in this particular case, the relative rates of that competing process with the process that you want is favorable for the process that you want. So there is a restriction if you're doing a crossed aldol reaction, even if you use one component that cannot be deprotonated, the other component, which can be deprotonated, could react with itself before deprotonation. And so only in those cases where just what you want is the fastest process does that type of reaction work. Now, these aldol reactions that I talked about, they've always been between two molecules. Here you've got benzaldehyde and acetone, so you've got two molecules. But you know that you've come across a few cases where one molecule reacts with another one, and in which, in addition to that intermolecular process between molecules, you could take the two molecules and join them together at some part so that the reacting pieces are still there, but they're joined together. And then you can join them and then make a ring. And you can do exactly the same thing with the aldol reaction. It turns out to be a very useful process. Supposing that you have this compound, which is a ketoaldehyde. Looks like that pen is rubbish. There's a trash can here. Oh, yes. Supposing I've got this compound, it's ketoaldehyde. Now, if I treat it with a base, I could deprotonate it here, I could deprotonate it here, and I could deprotonate it there. And if you do treat it with a base, 1, 2, 3, 4, 5, turns out that what you get is that compound, which of course doesn't look anything like the starting material. So, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Let's put the 7 there, just 1. Now, I label the atoms to give you a clue as to what is happening. But let me talk you through this. We have a compound, 2 carbonyls. We're going to treat it with a base. Let me write down that in fact we put a base there. We're going to treat it with a base. Now you know that if you take a carbonyl compound and treat it with a base, 2 things can happen. The base is a nucleophile, and the nucleophile could attack either of the carbonyls, because anything with a pair of electrons can attack this carbon or it can attack that carbon. So that's one of the things that the base can do. But you also know that if you've got a carbonyl compound with hydrogens on the alpha carbon, in other words, on the carbon next door to the carbonyl carbon, those hydrogens, or at least one of them in each case, can be removed to form an enolate, or a carbanion, negative charge on the carbon. So here we could make an enolate here, we could make a carbanion here, carbanion there, carbanion there. Now those carbanions could do various things. Each of them could attack a carbonyl in another molecule. Or some of them, perhaps all of them, could attack a carbonyl in the same molecule. So first of all, there's a competition between intermolecular processes and intramolecular processes. Now usually intramolecular processes are a good deal faster than intermolecular processes. Why? Because the 2 ends in an intramolecular process are already close together. So it's easy to understand that the most likely reaction is an intramolecular process. In other words, one of the carbanions, either this one or that one, is going to attack the other carbonyl. Now the question is, which is going to be the fastest process? You see, if the carbanion here attacks that one, we'll get a 1, 2, 3, 4, 5, 6, 7 membered ring. The carbanion here attacks that one, we'll get a 1, 2, 3, 4, 5 membered ring. The carbonyl here attacks this one, we'll get a 1, 2, 3, 4, 5 membered ring. Now the first steps in these reactions are reversible. If a hydroxide ion attacks this, remove a proton, the resulting enolate can remove hydrogen from water. So the first step's reversible. If any of these carbanions attacks the other carbonyl, that step's also reversible. It only becomes irreversible when the resulting aldol is dehydrated to generate the double bond. And it turns out that the fastest process is the one in which that attacks that carbonyl to give you an aldol, which I can write up. So the intermediate aldol is this, and that then loses water. So the formation of a 5-membered ring in this case is the fastest process, and you can get very nice yield of the cyclized material. So this is a way of making rings. Now there's one other method for making rings, very important. It's the Robinson annulation. Now annulation just means business of making rings. And the Robinson annulation was the method developed by Sir Robert Robinson, who was a Nobel Prize winning organic chemist working at Oxford. And the Robinson annulation is used in many different situations, but one of its most important situations is to make 6-membered rings. And the reason why it is the most important application of the Robinson annulation is that 6-membered rings are very, very common in all sorts of molecules that are very, very important. You've all heard the word steroids. Steroids got loads of 6-membered rings in it. And many of these steroids or steroid hormones are very important. And so I need to tell you about the Robinson annulation. If you start off with this compound, it is a beta dicarbonyl compound. Because if you start saying, you can start numbering from either of carbonyls, but if you start here, that's the alpha position, so that's the beta position. So that's a beta dicarbonyl compound or 1,3 dicarbonyl compound. And you already know that those compounds exist very largely in an enolic form. I've written it in the ketone form. But if you treat that with sodium hydroxide, you will get the enolate. All I've done is to remove the hydrogen from this position, and I've drawn a different resonance structure in which the negative charge moves here and then out onto oxygen. I've got to add methyl group there. Now, the next step in the Robinson annulation is to treat the compound with this, which is called methyl vinyl ketone. And you can see why it's called methyl vinyl ketone, because it is a ketone. It's got a methyl group on the ketone carbonyl and a vinyl group also on the ketone carbonyl. Now, what happens is that the electrons move like this into the double bond to give you that enolate. Now this is a new process for you, because you have not yet seen addition of a nucleophile to the beta position of an alpha-beta unsaturated carbonyl compound. That's the alpha position, that's the beta position. Because everything I've told you about carbonyl compounds so far in their response to nucleophiles has been that either the nucleophile, if it's a strong base, will remove the proton from the alpha carbon, or the nucleophile will attack the carbonyl. And so you might expect that the negative charge here would attack that carbonyl. It turns out that there's a faster process that goes on. What it does is it attacks this carbon, the electrons move here, and then out onto the carbonyl. So now we've made a carbon-carbon bond, and we have an enolate. Now that enolate can do various things, and one of them is it can remove a proton from water. And if it does that, water or methanol, whatever protic solvent is used, if it does that, you get back that tricarbonyl compound. And I'm going to write that tricarbonyl compound in a slightly different way. I've just spun it around that carbon-carbon bond. It's the same molecule. So what I've done is I've joined this beta diketone to this methyl vinyl ketone. Just join them together. Now I've got a compound that's got 3 carbonyl groups, and it's in the presence of a base, hydroxide ion. So the hydroxide ion could attack any of the carbonyl carbons, but it could also remove a proton adjacent to any of the carbons, this one, that one, or that one. And all of those go on. But in the case where it moves a proton from the methyl group, something else happens. This carbanion attacks the carbonyl. It can attack the other carbonyl there, but because of symmetry makes no difference. Wait a minute, I've dropped the carbon. Where did it go? Oh, the ring size was a bit wrong. Here we are. This is now all correct. You can see I've now made a ring. There's a negative charge on this oxygen. I know, yes, this is right. Do I need to write down again anything that I put up on?
It's like, oh, too bad.
It was the starting material as a precursor of that. All right, let me write it down. Let's write it down, yeah. This is one resonance structure. So I join the things together. Then I pick up a hydrogen. So now I've got this. This is the same as this. I've just twisted around one of the bonds. I deprotonate 1, 2, 3, 4, 5, 6. I deprotonate here. There it is. That carbanion attacks the carbonyl. I've got this compound, and now I'm going to protonate that oxygen. So I've made another ring now. So I can just summarize what I've done by saying good. So I've started off with something I just have to call ring B. I've treated it with methyl-vinyl ketone and a base, and I've added on something that I just happen to have labeled ring A. Now the mechanism is a little bit involved, as you realize, because there are many steps, there are many possibilities, there are numerous reactions that are reversible, and then there's the last one that's essentially irreversible, and everything goes over to the product. So what we've done really is we've taken a carbanion next to a ketone, we make a carbanion there, it adds to this carbon, which ultimately you pick up hydrogen here, you then deprotonate at that position, which swings round and attacks the original carbonyl, to give you an aldol by an intramolecular process, and then you dehydrate the resulting aldol to give you an enone. This is a very, very important way of making six-membered rings, and you can build those rings onto existing cyclic ketones. This happens to be a special ketone because it's got two carbonyls, so the reaction goes very, very easily. You actually don't need two carbonyls. So long as you have an enolate and you treat it with methyl-vinyl ketone, then you can build up the ring in this way, and that is called the Robinson annulation. So I suspect that you would prefer not to hear anything more about aldol condensations. There's a lot of shaking heads in agreement, because there are so many steps involved in pushing these arrows to understand what's going on. With a bit of practice, it turns out it's all very straightforward, but you need to think a little bit, because usually there are several places where deprotonation can occur. Usually there are several carbonyls. There are several ways where cyclization could occur, or where intermolecular processes could take place. Either this enolate reacts with that key carbonyl, or enolate from this one reacts with that carbonyl. It's a little bit complicated. And I've given you today and in the last lecture, I suppose, the most important examples. What I want to do now is get on to the very last topic of the course, which is much lighter and much easier, and that is the business of talking about substances called phenols. My first contact with a phenol, some phenols are antiseptics. My first contact with a phenol was when I was about 12, because I was very interested in athletics. The reason for that was that there was a very famous Englishman called Dr. Roger Bannister, who at that time was the first person in the world to run a mile in under 4 minutes. He used to skip lectures occasionally for training. It was very, very clever. I wouldn't advise any of you to skip lectures for training. And so I was very interested in athletics, and I was training. And my younger brother was pacing me on his bike, and he went in front of me, and I swerved and I tripped, and the spikes from one leg caught the muscles in the other leg and sort of ripped out some deep claw marks. And my mother took me to the local pharmacy, who then put some phenolic stuff on the wounds, which stung like crazy. Of course, I could have had to pretend that it didn't hurt. It hurt. And I was very lucky, because that's probably not the best treatment. Should have given me something more serious. But anyway, it took years for the scars to disappear, but I did run a mile in under 4 minutes. But then I didn't have the advantage. Dr. Roger Bannister, every stride was 7 feet. That's pretty big. He was an extremely tall fellow. At any rate, I'm going to tell you about phenols. Since that encounter with phenols, with a particular phenol, I've learned a lot more about phenols.
We have to survive finals. I think this is why I always do better second semester, is because you don't have to look forward to Christmas when you're done finals.
You just it's just like summer.
Yeah.
It's just, 4 months long.
So you're like, man. I think that's why. It's because I'm too focused on like doing everything else. And I want to go Christmas shopping so bad, but I'm like telling myself no. I have to study.
I have so much to study.
I kind of feel like we've done phenols already, but
We've done a lot of like benzene.
Is phenol itself, and you see that the parent substance, phenol, is simply a benzene ring with a hydroxyl group on it. And I want to point out something. I'm going to use little dotted lines to identify what I want to say. You'll notice that that structure has an OH on a double bond. And I've told you in the past that if you have an OH on a double bond, say this, it's called an enol. And I've told you that enols exist almost exclusively, in most cases, as the corresponding keto form. And so you might wonder, why is it that this stuff, phenol itself, doesn't exist like that? Well, it doesn't. And the reason is that that keto form is not an aromatic compound. It does not benefit from the extra stabilization that is associated with aromaticity. So phenols, although in the normal way that we draw them, although they have an OH group on a double bond, they are not really enols. So that's a very simple phenol, the parent substance itself. You can have the OH group on polycyclic structure. This is called 1-naphthol. Now some of these phenols have trivial names, and of course they also have systematic names. So let's give you a few of these names. You can call this one either parachlorophenol or 4-chlorophenol. The more systematic version is 4-chlorophenol. You notice the benzene ring has a chlorine on it, it's also got an OH on it, and you can guess from the fact that we describe it as a chlorophenol, you can guess that the phenol portion represents the principal functional group. This would be 2-nitrophenol. Or ortho-nitrophenol. Bromophenol. Or meta-bromophenol. The compound I've just written is 2-methylphenol. It's also got a trivial name, orthocresol. This one is 3-methylphenol. Or metacresol. And of course there's 4-methylphenol. Or paracresol. Now all the compounds I've shown you have just one phenolic OH. So the question is, can you have compounds with more than one phenolic OH? And the answer is you certainly can. And this is 1,2-benzene diol, and it's got a common name, it's called catechol. and the 1,3 has also got a trivial name, 1,3-benzene diol. It's called resorcinol. And finally, one, 4 benzene diol or hydroquinone. Now let me write that neatly. Rubbish. Hydroquinone. So you can see that many of these simple phenols have trivial names. It's a memorization job. The way you name a phenol is to name the compound as a phenol and then put some prefixes with a number and the name of the groups that are on there, at least for simple groups. Where you have very simple groups, the fact that the compound's a phenol takes precedence over other considerations, and you name it as a phenol. There are cases, of course, where the benzene ring will have a group that's more senior to the phenolic hydroxyl, in which case you name the compound according to the nature of that group, and then the hydroxyl, the phenolic hydroxyl, is named as a substituent. There's one example that I can give you straight away. This compound, you see, is both an acid and a phenol. It turns out that an acid is a more senior group than a phenol. And so that thing would be 4-hydroxybenzoic acid. So you know something about naming simple phenols. You also know that you can have more than one phenolic hydroxyl on the benzene ring. You can have several. But the only ones we need to deal with are the cases where there are 2. If there are 2 hydroxyls and they're in the ortho position, it's 1,2-benzene diol or catechol. If they're in the meta position, it's 1,3-benzene diol or resorcinol. And if they're 1,4, it's 1,4-benzene diol or hydroquinone. Now, one of the things that you need to know about phenols is that they're quite easily oxidized by air. And if you eat an apple and you do what I do, you have a working lunch. So while you're eating the fruit at the end of the lunch, you're also working, and that means that you might eat quite slowly. You might take a bite of the apple and then type away on your top-of-the-line Macintosh computer, writing some new publication to announce your discoveries in the last few days. And so the apple will stay sitting by the side of your desk for a little while. You'll notice it gets a bit brown. And the reason for that is that some phenolic components are being oxidized to colored substances. Okay, enough about naming of phenols. I want to say something, first of all, about how to make them. Now, you already know one way of making phenols, because when I talked about diazonium salts, I pointed out that you could take a diazonium salt and you could convert it into a phenol by treating the diazonium salt with copper oxide and water. So let me just run through that again. Phenol itself, by the way, was the first antiseptic that was used in hospitals in England. I mean, it was the first antiseptic used in hospitals. It happened to be in England that was done. And if they were slicing you open to do an operation, they would squirt phenol solution all over in the air, because it didn't do the doctors much good. But that was the beginning of attempted sterile control in operating theatres, because before the age of modernish medicine, if you had an operation console, you'd die of some sort of infection. But it was found that phenol itself was helpful in controlling that. So what's a laboratory synthesis of phenol? Well, let me give you a particular example. If you treat this substance with sodium nitrite and sulfuric acid at about 0 degrees, the organic piece that you generate is this compound, as I indicated in a previous lecture. And if you then treat this with copper oxide and cupric ions and water, what happens is that the diazo group is replaced by a phenolic hydroxyl. So whenever you see a phenol that you need to make, one of the things that you need to consider, one of the questions you need to ask yourself is, can I make this phenol via a diazonium salt? If you think you can, you then have to ask yourself, can I make the appropriate aniline? And then one of the questions that follows that is, can I make the corresponding nitro compound? And if the answer to all that is yes, then you can make the nitro compound. You could reduce it with iron and HCl to the aniline, diazotize the aniline to the diazonium salt, treat the diazonium salt with copper oxide and cupric ion and water. So that's a laboratory synthesis of phenol. Now, I have not used this expression, a laboratory synthesis, before. Why do I use it now? The reason is that phenol is made on an industrial scale. And there's no way that in industry they're going to make huge ton quantities of diazonium salts. For this purpose, they make phenol in a different way. And the industrial preparation of phenol, there are 2 of them. I'm going to give you only one. If you take chlorobenzene and you heat it with sodium hydroxide, 350 degrees centigrade, you get that sodium salt, and if you treat that with HCl, you get the phenol. Now, how does this happen? Well, probably, notice I'm saying probably, what happens is the following. Under these incredibly brutal, harsh conditions, what you get is a substance called enzyme. for which I've written a bunch of resonance structures. And now, we're going to write it.
What is he drawing now?
So probably people believe that benzene is involved. You know why it's called benzene? Relates to benzene, and it's related to acetylene, because one resonance structure, that's triple bond. Okay, I think that's enough for today.